Okay, so welcome to the afternoon session and the last session of the school before the discussion meeting starts tomorrow. This is Martina, like with her second talk.
Thank you. Thank you for this introduction. And so I have the difficult task to prevent you from falling asleep after this nice lunch and the warm weather. So I will resume my lecture where I stopped yesterday, maybe a bit before, by making a very, very brief summary. Remember that I talked yesterday about quadrupole traps, and in particular about traps which are working with radio frequency or with oscillating electric fields in order to trap particles. These traps are very versatile. They can be used for many different applications, for many different charged particles. What I will do today is I will finish off my part on radio frequency traps and then go and present you another trap and the experiments which can be made in this other trap, which is the penning trap. But before doing so, I will just give you the last part of the radio frequency traps, which is the more technology part where radio frequency traps have evolved into since the last 10 or 15 years. So remember that we've seen yesterday that there is the motion of a particle in a trap can be described by material equations. We can look at where there are stable solutions as a function of the experimental parameters. And I have also introduced one of the main issues or of the main items in a radio frequency trap, which is a strong confinement regime, where we can go to a regime where the particle is stored in or localized to a space which is small compared to the wavelength it's probed by. Okay, so if we want to go to this strong confinement regime for all our precision experiments, what we need to do is we want to have very high motional frequencies. We've talked about that yesterday. And in order to have very high motional frequencies, we need very high trapping frequencies. So very high trapping frequencies means frequencies which are above 10 megahertz. Often it's even beyond, like 20, 23, 24. But there is a technical issue. Well, there's a technical issue with that, because in order to fulfill our stability conditions, we not only need, if we have these high frequencies, we also need amplitudes of these fields which are of the order of, let's say, beyond 1,000 volts. And having these amplitudes with these frequencies and applying that to a macroscopic structure is a technical challenge because of capacity reasons, okay? So it's very difficult to maintain these high frequencies with these high, with high amplitudes if the capacity of the structure we use, of the trap we use, is very high. So what we have to do is we have to go to low capacity traps, and going to low capacity traps means traps which are small, okay, where there's not a lot of macroscopic structure, but where there are small structures. And I've introduced yesterday already, I've already introduced these miniature traps, which
uses, like, let's say, trap frequency around 25 megahertz, and they also, as you said, they also use large voltage. So is there any particular scientific motive that using, instead of, let's say, 10 megahertz going to 25 megahertz there?
Well, it's the fact that you want to go to the strong confinement regime. Okay, if you want to go to the strong confinement regime, if you write it down, you have to have high motional frequencies, high secular frequencies. And these high secular frequencies, you only have them because omega is proportional to large omega. Then you have to have high trapping frequencies. If you work on ion clouds, for example, you can have a drive of whatever, 1 megahertz, 2 megahertz, 8 megahertz, if you don't mind having lower motional frequencies. Lower motional frequencies means a more shallow potential, a potential which is more open and which cannot be very steep, okay? So what you want to have is really If you are okay with that, because I mean, we have a trap, for example, which works on 8 megahertz. And you don't, I mean, if you don't want to work on a single line or on a very localized sample, you don't need very high frequency. And Tanya wants to comment.
I just wanted to add one thing to Martina's answer, because I interpreted your question a bit differently when you ask why do people go from 10 or 16 megahertz to 24. I think that what you're pointing is also the mature parameter Q. So because when you go to higher frequencies, you push down your Matthews Q parameter to way below 0.1. And that's actually very good for the stability. So if you want to put more ions who have a long lifetime, the lower the Q, the better.
Yes.
So the reason that many people don't go to extremely high frequencies and trap drives is a technical one, because it gets really difficult to build this helical resonators at 50 megahertz and so, and you need a lot of, it comes at the cost of putting a lot of voltage, like thousands of volts. That can be ugly, but in principle, it's a superior regime. You know, if you go to a very low Q parameter, then you have a very big stability.
And as I said yesterday, there has been this famous experiment at NIST also, where they had a 120 megahertz drive, but coupled with an antenna. It's more, it's about also technical limitations, okay? Because a vacuum feed through is always a capacity which will break down this helical resonator performances, okay? And so it's important that, I mean, there are people thinking around other ways to do, and going to small, I mean, if you want to work out things on this queue, then you can juggle with the different entries. And one of the things is to go to small R if you have a smaller VAC, for example.
Yeah, so I was just going to say the same thing. So why not just have small Q omega and also small?
You can have
Is
small
the-
everything, yeah.
Yeah, and VAC you could be at a lower value, right? So what is the problem with that? There must be some problem, right? I mean,
No,
I could
there's no
choose. I
problem.
could choose my omega.
No, the problem is that if you want to work with a macroscopic trap, okay, if you the traps I've talked about yesterday, they're macroscopic. That means they have sizes of a few millimeters, and their capacity is larger than those of the traps I will talk about now. Okay, I will show you some traps which are very small, and they have a negligible capacitance, if you can say so. And so the only thing which is more important then is the vacuum feed through, okay, which is still limiting for the helical resonator. But having small structures is also a way to be able to better optimize things. I mean, if you want to control your thing by computer, by everything which goes up to 10 volts, for example, then you need to go to small structures, because larger structures, you have to apply larger voltage. So there's no real problem, but you have to think about the dimensions of your system before you start working on it.
Yeah, so I understand that. So what I'm asking is that I have a VAC divided by omega squared. So I could also lower my frequency and lower my VAC to keep the Q parameter.
But
as
the
I
omega
want.
is squared. So you can, I mean, you need a certain, I mean, there's a trade-off, okay, between all these values. And then people tend to, for laser cooling experiment, for example, people tend to aim something which is between Q equals 0.1, 0.2, okay? Because you want to have a certain well depth, but you don't want it to be too deep, not to heat the ions, okay? So there's a trade-off between different inputs.
I think he's picking on one thing that is missing on the slide. You need another equation to understand his question, because what we see here is just Matthews Q parameter. And you're totally right that you only have to look at the ratio V divided by omega squared, and then you can get any Q you want. But now the question is, what would it mean for the secular frequency in your ion trap? And if you look at the equation of the secular frequency, omega, small omega, is Q divided by square root of 2 times omega.
This
And you
is,
see at the same Q, at the same stability, suddenly you have a very different secular frequency if you play around with the omega. This is not independent of each other.
but I hope that all the attentive students remember that this was the slide before. So when I talked about that yesterday,
That's the test.
I walked you through there, and it's true that there is omega, which is which is proportional to the large trapping frequency. Okay, so you should look at what I told you yesterday. And then afterwards we can discuss, okay? So now I start. Because what I wanted to do, if ever this works, but it does not, so I do it like this. What I wanted to do is I was briefly talking about miniature ion traps, but I will in particular talk about the microfabricated trap, because today, for different reasons, and one of the different reasons is working with higher frequencies, lower voltages, being able to better control also by computer. This is one of the reasons, and to go to very small traps. The other one is also to be able to design your trap in a way that it can be as versatile as possible. And one of the, I would say, pioneering proposals in that sense was this paper where Dave Wayland had put forward the idea of a quantum CCD or something which has a sort of spatial arrangement in a certain sense. And then there has been this, apparently, oh, this is the problem. It's off. Now it should work. Okay. Okay. So, and in this proposal, you will see this is the proposal of this sort of scalable architecture that if you want to work with individual ions and be able to manipulate them just as you manipulate bits in a classical computer, if you want to control the qubits in a quantum computer, then you have to be able to have access to them individually, to control them individually, to manipulate them individually. And you cannot, and this will not be possible if you have either a large ion cloud or something, a large structure where it's difficult to make the separation of these ions. So one of the ideas is to work with these sort of distributed architectures which allow to transport ions to a certain place, bring them to an analysis zone, excite them, bring them maybe to another interaction zone where they can be entangled with another ion, bring them back to a readout zone, and be having an architecture which allows to transport, to manipulate, to control individual ions on a structure. And you can easily understand that if you try to make a 3D structure in a certain sense, this is not possible. I mean, this is really, this becomes very complicated. So one of the ideas was to go to a 2D structure. So we're going far away from the initial Paul structure, from the quadrupole thing with the equipotential lines, but going to a 2D structure, which allows with a certain number of electrodes to produce a potential which is close to the one that of a ideal Paul trap, and which allows this manipulation, addressing, and control of individual lines. These traps, like what we said yesterday, is what's always important for these traps is we need to have a potential that confines. We need to have a zero potential line where the ions have or experience the minimum of micromotion in this potential, so that we can that we can always be in this strong confinement regime, which allows us to get rid of larger Doppler broadening effects. And so the idea was to go from a sort of a 3D structure like you have in here, this rod trap, to project that on the plane, and with these rods try to be able to make the same potential or almost the same potential as in that 3D structure. And you see that, well, there are, in principle, you go from that 4-rod structure to a 5-wire trap because you need to have a certain symmetry also. And this is something, this is the basic, I would say, this is a slide which has has also some years of age already, but the principle is there. You want to be able to make a potential with smaller voltages, but still be able to trap. And if you see, you can write down the potential of these sort of structure and also simulate or model the behavior or the potential which is produced by the structure, and which comes close, which comes close to what we have an ideal Paul trap. In particular, as I told you, in the Paul trap, you have this harmonic potential. And here you have potentials which are more or less harmonic, at least in the center of this, of this trap. Of course, parameters are different. I will not go through the details of that. No, this is maybe too much. I will not go through the details of that. The parameters are different, of course, because as you see in here, for example, there are many more than these 5 or 6 or whatever electrodes because of different ideas. But why are there many more electrodes? Because first thing is, oops, sorry, you see that in here, in this very schematic setup, is that all these black boxes there are different electrodes. And in principle, you could think, okay, I make plus and minus, and I will try to have my potential between these pluses and minus. But in between, there are often also compensation electrodes, because the potential we create with a structure like that is never ideal, okay? So we always have to try to correct things. And so one of the ideas is to put additional correction or compensation electrodes on that, okay? Also to be able to correct any deviation which appears during the use of these traps. A trap is always aging, okay? You will create ions, so you can have, for example, if you create ions close to the surface somewhere, you will have maybe an oven of your calcium or whatever ions. You can have a deposit of just a very tiny deposit of neutral calcium on your surface, which will modify your surface, which will modify the potential. And the condition we talked about yesterday, being close to the zero potential line, is very stringent. So you have to be able to push your ion really to this center zero line, and also to correct for certain effects in your trap if your trap gets distorted by any means, which can happen also, well, either during the realization or during the setup of your trap, but also during the use of your trap. A trap can, in the course of the years, can have different problems because there are some deposits on some sides, and there can be asymmetries which come up. So if we come back to this picture, for example, so this is a picture from the Sussex group. There are different other realizations I just wanted to show you. So if you look at this part, for example, you see this is already something which goes around a certain corner. Today, there are other corners which are a bit less edgy, okay? So there is a lot of work going on these microfabricated traps in order to make them as ideal as possible, and in order to avoid as much as possible the ions to heat up in these structures, okay? So this is one of the first traps in Sussex, as I said. So you see the different electrodes here. The ions can sit in between there. They can be shuttled around. There is a large bunch of work of people having worked about transporting ions without heating them. Because, I mean, normally if you transport something, you put some energy in there in order to push the ion to a certain place, and that the ion can pick up that energy. So there is a lot of work about what we call the shortcuts to adiabaticity. So you can be adiabatic, but very fast. And this works very nicely. And so it can really help to speed up the control and manipulation of the ions in these traps. I have some other pictures. This is from this. So this is one of the very first sinusoidal. This is 2006. You see, was one of the very, very first microfabricated traps. One of the real, I would say, pioneers. You see, there's just a few electrodes ground there. The difficulty in these traps is also they're 2D. So all the upper part is open, which is very nice for you put in your lasers, and just above the surface, you can look in there. but it's also, the potential is very fragile in a certain sense, okay? So everything which is all the environmental effects can of course perturb this potential because there's no other electrode which will close this up. This is a 2D trap. This is just a surface. This is a 2D trap. And there are others, maybe I think I have, this is just a planar trap chip, okay? This is a 2D trap, but I think I have another one from Ferdi. Sorry, above the surface. So there is, the trap is really, it's really a plane, okay, with different electrodes, and the ion is sitting above the surface. Okay, normally, well, it depends on the potential, it depends on how the trap is designed, but the distance to the surface is something between 20 and 100 micrometers, more 20 and 50 micrometers. The potential you make here, okay, the potential you can make here, I think you see that on this, oh, maybe here. The potential you can make here is really something which is, I mean, it's not, it goes off from, there's a certain distance from the surface, okay? You can really calculate your potential, and normally you have something, yeah, like I say, the distance is something which is about, yeah, here it's even large. You see, this is 0.5 millimeter, which is a lot, okay? This is also, it's already an older slide, but the idea is the same. You have this potential and you can tune this potential by designing the electrodes and by designing, of course, the parameters you put. Okay, so let me go back. So this is a real 2D trap. This is one of the racetrack traps on NIST, which is a plane structure, and which allows also to shuttle the ions all around here and to have different interaction zones. And one of the traps I want to show you, so this is a microstructure trap, but this is a 3D trap, okay? This is a 3D trap in a sense. You see that the ions are sitting, so these are different parts, okay? So you have different distances, and as you have different distances, even if you put the same radio frequency on that, you have different potentials, okay? And so you will see this trap there is a real 3D structure. There's 1, 2, 3, 4 rods or electrodes, okay? But on 2 microfabricated electrodes, or which can really see, you see here is this is the size, 250 micrometers apart. Here, 100 micrometers apart, 100 micrometers across, and 250 apart. So this is really a small structure, and these structures are today made like all these micro-fabricated things. They're made in the clean rooms with a mask on a certain chip, and they are really produced. They can be produced in a more or less industrial way. There's a first industrial ion chip, which is made by Siemens in Austria, because the idea would be to have something which is standard and reproducible, and not have these homemade traps that we all have in our labs, but to be able to build tomorrow's quantum computer with a standardized chip. Okay. So this is just the idea of, I'll still have more. Okay, but now you've seen the idea is going to a very small structure, going to a structure which is standardized in a certain way, and being able to finally to confine as many ions as well, almost as many ions as you would in a larger trap, but to have strings of individual ions in these sorts of. Okay. I might have a very small excursion on heating. These traps do have some heating issues due to different effects, because, well, what we talked about yesterday is that radio frequency heating is an issue, and here can be other heating effects which come to that, like, for example, electric field noise or other environmental sources. So there is a larger effort of different people who are working on who put together data from different traps on different sites and different configurations in order to see what might be also, and also to come closer to what might be the reason why there is this noise and to get over. Okay. And one last idea about that. Wolfgang Lange started that a long time ago, maybe 10 years, and now it's taken up by many different groups. That if you have already a microstructure trap, which is fabricated in a more or less standardized way, you can say, okay, why, if I do have a microscopic trap, why would I have a macroscopic optics on that and come in with my lasers from all the sides and have a large objective on that? And so there are people who are making efforts to bring the optics into these microstructures also, to come in with fibers, for example, bring in lasers, doing the observation directly close to the ions on these chips. So in order to come closer to integrated system and to be really much closer to the ions on the chip, and to try to reduce the, what we call the physics package of these setups. Okay, but I will stop there about radio frequency traps, because this was just the final last annex on that. Okay, and I will switch to different sort of trap. Okay, what we've seen until now is the how to trap ions with an oscillating electric field, things that different sorts of trap, which are, as I told you yesterday, used for a number of applications, be it frequency metrology, quantum information. These larger multiple traps are used a lot in cold collisions, reaction rates. There are people who are making also, who try to superpose cold ions in a linear trap with with cold atoms from optical traps. And so there's really, that's a very dynamic field around these radio frequency traps. But there's another sort of trap, which, as you remember, shares the same ideal geometry, but has a different sort of operation, of course, because we don't have oscillating electric fields anymore, but we have magnetic fields. And as you will see, these traps, which have magnetic field and which are called panning trap, these traps have also different application. They use differently. They use differently for different reasons, for reasons which you will see. They're a lot used in mass spectrometry, where they can give really extremely good precisions. And I will now present you how that works and what it's used for. Yes.
Before you move on, in the earlier slide, those fiber cavities you showed.
Yes.
So two questions, like how that curvature is made and what kind of finesse do you get from those cavities?
How the curvature is made, they're polished. Okay, as far as I know, what is today is made, they're fabricated and polished in a certain way. Okay, they're used for cavities also. What's the finesse? I don't know. Tanya, you know fiber cavities? No. Well, we can look it up. It's fiber cavities there's a number of people working around these, and I could not tell it. And it's probably on the wavelength also. Okay, now going to the panning trap. Okay, there's something missing, which is the panning trap and its B field. What does it mean? Okay, so you've seen that yesterday, the same quadrupole structure as the Paul trap. Okay, the equipotential lines. Okay, that's we start from this ideal structure always. And you see that what you've seen for the radio frequency trap, we can go far away from that ideal structure, but still have very good trapping conditions. Okay. But if we start about the panning trap, so we have the same, exactly the same equipotential lines, these two hyperbolic end caps and the ring. But what we do in the panning trap is apply a magnetic field along that z-axis. Okay, applying a magnetic field along that z-axis with charged particles will make the following. It will force the ions to circulate around these B field lines. And as I will turn around the B field, rotate around the B field lines, they will just be trapped and they cannot go somewhere else. Okay. Well, they could eventually spiral up or spiral down, but in order to keep them in that trap, okay, what we do is we apply a DC voltage on the upper and the lower end. Okay, so that's as easy as it gets. The problem is that you will need the magnet. This is the one large difference between the radio frequency trap and the panning trap. Okay, is in the radio frequency trap you need the resonator, you need a helical resonator, you need to have your drive frequency, but in the panning trap you need a magnet, and the magnet has to be, well, it depends on the size of the trap always, but the magnet is a few Tesla. Okay, a magnet of a few Tesla is not something which is small like that. A magnet of a few Tesla is normally a can, which is like, Dima showed some this morning, which are maybe even larger, but a magnet of a few Tesla can be a nice little machine which you have to fill with liquid helium to keep it cold. Okay, so I introduced yesterday already Hans Demert, who has been the person who has worked around this up. Really, I cope with my slides. Okay, Hans Demert, who is the person who has really put forward all this panning trap and made a lot of very pioneering experiments also in the panning trap and for radio frequency traps too. So that we have to say. So if you look at the panning trap, then as I said, there is a trap charged particles, you have a B field, and then you have a Lorentz force, and the trap is, and the charged particle goes around the B field line. So this is something which you have learned in your undergrad physics. And here's my trap. I'm sorry, it's in different parts. And we can write then down the equation of motion for a single particle, okay, in this potential. And what we get out, trust me at the end, or trust Richard Thompson and other people who work on that. So what you get out at the end is the different frequencies of the ion in that trap. And you can easily understand that there is the cyclotron frequency, which is something which is due to the magnetic field, okay? So of course, depending on the strength of your magnetic field, you have different cyclotron frequency around the B field lines. And you have this, what we call the magnetron frequency, so this other frequency, which depends on the voltage you put on that and the geometry of your trap, okay? So there are two frequencies, and maybe I think I have it on the next one, yeah. No, in fact, we have 3 types of motion because there is, well, we'll go through there. Okay. So we have, the first thing is what we call the axial motion. The axial motion is the motion which is due to the DC potential that you put on the end caps. Okay. So this is something which is, which you can, it's a harmonic motion. That's something which you can easily calculate also. That is something which is the axial motion of the ions in the trap. Then you have to see that what we have is, the first thing we write down is, what I write down is the modified cyclotron motion. Why is that the modified cyclotron motion? Because you can, what you see here, you will see that you will find that omega z term also in that modified cyclotron motion, because of course, the different types of motion in that trap will not be decoupled, but there is a coupling of these frequencies in the trap, okay? And so what you will find in that modified cyclotron motion, which is more or less the orbit around the magnetic field line, but with a certain contribution due to that axial motion, okay? So you will find this in there in this modified cyclotron motion. And if you go on coupling, and if you go on looking at the couplings of these motions, then you have what we call the magnetron motion, which is really the E cross B field drift, okay, the E cross B drift, okay? So you have not only do the ions rotate around the B field lines, but they will also rotate around the center of the trap, okay? So we do have this radial motion where you see that they do have this spiral motion around the B field lines, But in addition, they will also have this E cross B drift and go around the whole trap. Okay? And so you will see that these motions are not uncoupled. Okay, they're coupled together because of also of the geometry of that structure, and we will see that in the following, that it's sort of nasty that they're all coupled, but it has some good also because we can use the fact that these frequencies are coupled also in the trap. Okay, so you have the axial motion along the z-axis, and you have that radial motion, which is in fact a two-component motion with a smaller, you see the smaller radius and then this larger radius going around the center of it. So if we go, so you can write down not really the stability parameters like for a Paul trap. Okay, this is very different, but we know that what you can show is that the trap becomes unstable when the magnetron and the modified cyclotron motion becomes equal. So when omega c squared equals 2 omega z squared, then the trap becomes unstable. So you have to design your trap in order to be able not to fall into this regime. So when we look at the expressions of the three oscillation frequencies, I put up a photo of Jerry Gabrielson because he worked a lot on that. I mean, we talk about the invariance theorem, which is called Brown-Gabrielson. I think I've never met Lowell Brown, but I often met Jerry. So this is Gerald Gabrielson, who worked on this, who worked out this Brown-Gabrielson invariance. What Jerry could show is that there is a condition between all the frequencies, okay? And the fact that there is this condition that this condition holds, even if the trap has slight imperfections or slight misalignments, okay? This condition still holds. And this is something which is very useful because it allows us today to make very nice and high precision measurements. What we do in these traps, we measure frequencies to measure masses, okay? And so if you see that if the frequencies are coupled, you don't need at each step to measure every frequency, but you can measure just some frequencies with high precision, and you can deduce the others, or you know that there's a stable relation between the frequencies, okay? So it's very important to have this invariance theorem, and it's a lot used, and also in particular as it holds also for traps which are not always perfect, and that makes possible the very high precision measurements that I will show you. So, well, if you put then ions in the panning trap as in the Paul trap, I mean, if you put more than one ion, you always have space charge effects. You have Coulomb repulsion between your ions or your electrons or whatever you put in there. I mean, if you put charged particles, they're all charged, so you have Coulomb repulsion. And if you have Coulomb repulsion, you also have a sort of a space charge effect because there is a space charge which is building up, and then that will slightly modify your potential. In panning traps, all cooling methods are applied, okay? When I say all cooling methods, there are many people who are using buffer gas cooling. There are many people who are using laser cooling, but laser cooling in a panning trap is a bit more tricky than a Paul trap because of the orbits which do sometimes behave counterintuitively due to the coupling. It's not always the fact that if you go to lower temperatures, not all orbits will shrink and come to a better localization. There are some orbits which will grow at lower temperatures. So you have to be very smart to do the laser cooling in the panning trap, but I will not go into the details. If you want to look it up, you look up all the papers which have been made by the group at Imperial College, Richard Thompson and Danny Siegel. So what I will show you later on, that if we have large ion clouds, we can really have very large ion clouds, and they behave like a non-neutral plasma, like a one-component plasma. We talked about that yesterday already. And then these one-component plasma, they are very interesting because they have some very nice features. They have uniform density, they have sharp edges, and well, they rotate around the z-axis, okay, because everything rotates in the panning trap, but I will tell you how to get around that. And the most important thing, the panning trap has no micromotion, no trapping field, no oscillating trapping field, no micromotion, no driven motion, okay? So, which is a real advantage for certain, okay? The fact is that in a panning trap, if you get something very cold, it more or less stays very cold. In a radio frequency trap, due to the micromotion, due to the driven motion effects, due to radio frequency heating, over time, ions will, or the trap particles will heat up. In a panning trap, it's much easier to go to low, well, it's much easier. Particles stay cold longer, and that has also some advantage. The inconvenience of the panning trap is you have a B field. And so if you have a B field, your lines are split, okay? And so you have Zeeman splitting and things like that, and which is not always very nice for high precision spectroscopy. But there are other things which you can do. There's not a lot of optical spectroscopy in a panning trap because you always have to look for the Zeeman effect, okay? But there's a lot of other spectroscopy applications. Okay, there are single particle experiments also in panning. And the main, or one of the main uses of a panning trap is mass spectrometry, okay? I think there have been quite a talks about optical spectroscopy in different forms during this week. There have been things about clocks and things like that, but mass spectrometry is something which is maybe even more present in our everyday life than optical spectroscopy, because mass spectrometry is used in a number of experiments and also applications. And for example, I know that in France, that all the fire brigades now, they do have a mass spectrometer, and this mass spectrometer is most of the time a trap, sometimes a radio frequency trap, but sometimes also. So traps, as we've seen, are mass selective. They have been made like that. I mean, they have been put forward like that to be as mass filters. You've seen that if you look at the frequency, which depends on the B field, there is the E over M in this equation. They're always mass selective, these traps, okay? And so what we can do, the first thing what we can do, if we have a sample in a trap, it can be purified. That means you can choose the condition that you trap one species and only one species, and not a number of different isotopes. Okay, so you can really have mass selective conditions to only trap a single species in your trap. And what you can do also is, if you have a species which is not known in your trap, you can measure the frequency, the motional frequency of that trap, of that species, of that particle in your trap. And this will give you an idea of what the mass is. Most of the time, the mass spectrometry is made with a reference ion. Okay, if you put something in a trap and you measure 250 kilohertz, that will not tell you whatever the mass is, okay, what the thing is. But if you first measure a reference ion, some of your favorite reference ions, and most of the time the favorite reference ions of most of the people is carbon-12, okay, because this is just the standard, and then you can measure the measure with respect to carbon-12, but you can put a carbon-12 ion in your trap, you can measure the frequency, and then you put an unknown ion in your trap, and you measure the frequency. And from the frequencies I've showed you, from the calculation of frequency, you can just calculate what the unknown mass is, or what the unknown E over M ratio is, and you know where you are, almost. These traps are all in excellent vacuum conditions. Most of the panning traps are in a magnet, in a cryomagnet. There are also some panning traps which are in a magnet with a warm bore. That means the magnet is cold, but the panning trap is warm. Okay, that exists also. but some of them are in cryo also. And we do have single particle sensitivity, and I can show you some of the experiments. And also what we can do in these traps, ions can be accumulated, and that's in particular interesting for the experiments where we have very rare or exotic ions. This is why these sort of mass spectrometer, they're used at some of the machines like Isolde, which is a facility at CERN which produces different isotopes of different radionuclides, and or Triumph. And so as we can accumulate ions and also individual ions, so you can, if you have a production rate of an ion per minute, and you can just accumulate for 100 minutes and just accumulate the ions in there and use that as a reservoir and also measure very rare and exotic isotopes. So this is something which I will just tell you a bit about masses. And I've also, I said that yesterday, but I maybe should repeat that many of these slides, I have used the slides from my colleagues from all around the Max Planck Institute for Quantum Physics, which is a major hotspot for these experiments. So they have, so these are some of Fabian Heiser and also from my colleague Richard Thompson of Imperial College. And you will see there the experiments I will show in antimatter. I will show you the experiment that Stefan Ulmer makes. Sure. So if you measure masses, and we're talking about precision measurements in this school. So if you measure masses, if you look at the mass of an atom, then you have what you measure in there is the masses of the elementary constituents, and of course the mass also of the binding energy. You measure the masses of the elementary constituents and the binding energy. And normally you have, well, the orders of magnitudes is something like that, okay? The mass of the neutron, for example, the neutron or the proton is, for example, is just below a giga electron volt per c squared, okay? Which means that is something which is written here, 10 to the minus 27 kilogram, okay? This is the mass of, well, approximately of the neutron of the proton, okay? And so you can split this down. If you split it down like a bit like in this, with this idea, okay? If you have the mass of the atom, so you have the mass n times the mass of the neutron, which is in that range, giga electron volt per c squared. The proton is the same. The electron is, you know that, it's much lighter, 2,000 times lighter. It's so you have the number of protons and minus the binding energy. And so the binding energies are of the order of something which is between the electron volt and the mega electron volt. And what you see, if you really want to measure down to these levels, okay, if you want to have a resolution between these values and these values, you need to measure something which is at least down to the 10 to the minus 10 regime, okay, measure masses down to these regimes in order to be able to distinguish these bindings energy, for example, with respect to these masses. Okay. So this is just an example. So there's, I have a number of examples. So this is an example for calcium 52, 52, 51, all of you know, I mean, we always say calcium 40 because that's what we're used to. So this is already a nuclide, which is a very, or a neutron richer isotope, okay? And you can, there have been, if you want to look for that, and I will show you how this is measured afterwards. There can be, in these panning traps, you can measure the difference of these different isotopes with a very high resolution. And so this is just an example for calcium. So where are these mass spectrometry experiments used? Well, if we go down from above, so precision is always relative. Huh? What do you call high precision? Well, in general physics and chemistry, you never, well, you always have precisions around 10 to the minus 5. If you go to the separation of isomers, for example, you need at least a precision of 10 to the minus 7 for your mass measurements. There are weak interaction studies. There are neutrino physics, for example, where you need to have resolutions about 10 to the minus 9. And the best tests we make, or people make about the CPT tests, or looking for QED in highly charged ions and looking at the separation of atomic states. You're looking forward to have a mass resolution of 10 to the minus 11. And these are things which can be made today in these panning traps with a very good approach. There is a very nice publication that Ed Myers has made 10 years ago, which is called The Most Precise Atomic Mass Measurements in Panning Traps. So if you want to look them up, well, it's already 10 years and there have been measurements since then. But that's a very nice paper which puts together measurements from different groups, and you will see which groups are working on what. And so you already have an idea of what have been the precisions 10 years ago. There has been some improvement on that. And of course, all these masses are giving an atomic mass unit. Yeah, I think that's something I cannot really explain it to you, but I think there's something about the binding energy of the constituents, which is different in the antiproton and in the proton. But I'm not a specialist on that. But yeah, it's surprising, huh? But yeah. Okay. Okay. So how will you measure? What is the way you measure in that trap, and how can you measure the masses? And you know that I think that Charlo once said, never measure anything else than frequency, because frequencies are really what we measure to the best precision. And this is what we measure here, okay? There are frequencies being measured. So an ion, this is a very large ion and very small trap, you see. So this is the discussion we had yesterday. Normally the orbit will be a bit smaller. Okay, so you have your charged particle in your trap, and then you have pickup electrodes, and you can image the image current of this charge in the trap, okay? And if you image this ion current signal, okay, you can then amplify that with a no noise amplifier and look at the Fourier transform, okay? If you look at the Fourier transform, you will get out something which has a nice frequency here, which is called the mass spectrum, with one nice frequency, okay? This is the most easiest and non-destructive approach of measuring a frequency in the panning. The charge will continue to oscillate or to orbit in that trap, and you can continuously measure image currents and continuously take data and look at your amplified signal in order to look at the spectrum. Fully non-destructive detection, okay? There are more destructive methods, okay? One of the methods is, of course, like in all the traps, we use that less today when we're working with optical detection. We used that a lot when a while ago, when we didn't have so many lasers in the lab, is the ejection of the ion onto a microchannel plate, okay? If you have an ion, be it in every configuration, a Paul trap, a panning trap, you can always eject your ion and look on the microchannel plate or on an electron multiplier. You can look, do I have a signal, okay? Which is a very reliable technique, looking for a charged particle on a detector. And so what you can do in this also, if you have calibrated the distance between your trap and your detector, you can also measure time of flight, okay? That means you just see from the moment that you eject the ion and from the moment you will detect it on your microchannel plate. If you have a lighter ion, it will be faster at the microchannel plate than if you have a heavier ion, which will take more time to come to the microchannel plate. So using time of flight spectroscopy is a way to also have a first approach of mass measurements in these traps. And it can be, you see, it can be quite, the resolution can be quite nice. It can be go down to 10 to the minus 9, because what you measure is the arrival time on a detector. Sorry? 7 Tesla. Where? This one? This one? Oh, this one. This is in the magnet. Yes, this is from the Max Planck Institute of Nuclear Physics, and this is a 7 Tesla magnet. Yes. You measure the trajectory. You have a trajectory of the ions, but what you're measuring is the time of arrival on the detector. Okay, if you want to have a mass resolution, you measure from between your ejection pulse and the arrival time on the detector. You measure this timing because this will be much more precise than the trajectory. How do you get the x-axis? But this is just the experimental setup, okay? So this is the real time of flight, having things arriving at a certain moment, being ejected and arrival. But this is the schematics of the setup because the trap is sitting in the magnetic field and which is rolling out, as your neighbor explained to you. So this is, sorry? Normally, well, there are different methods, but normally what you do is you put on a little extra pulse to eject them. Okay. How you eject it, it's of course has an importance of what will you detect. Okay, if you eject things by accelerating them a lot, then you have to take into account that for the time of flight. But time of flight measurements are also relative measurements. Okay, they are relative timing of arrival. Okay, so of course you have to make sure that your ejection pulse that not completely mix up any measurement you will make. But this is most of the time we do this is like by putting in an extra pulse and kicking them out. Yeah. Yeah.
133 hydrogens as opposed to 1 cesium. Has there been an experiment which sees whether the masses?
Exactly. We can. So what we do, that's a very good question because what we measure is always charge matter. Okay, we measure E over M, and there can be also species which are very close. Okay, there is, for example, if you look at N2 plus and CO plus, okay, that's the same mass. Okay, almost, because the binding energy is different, and there are still some differences. So if your resolution is high enough, then you might be able to detect the difference. And this is sometimes, for example, a way to calibrate also. In particular, using N2 plus and CO plus, okay, because they do have the same mass, but they are different. I mean, the one is symmetric and the other one's not. And so they do have different binding energies. And so this is a way also to see how good the resolution of your apparatus is and how good can you separate different species like that. But you still have, there's always I mean, you can have, if you, for example, one of the issues in there is normally you want to work with singly ionized ions, okay? But sometimes, depending on how you create them, they're doubly ionized, for example. And so what you look for is often you look at the modulo of what you see in your spec. The FFT will give you, and you will see if it's really twice. But this is real an issue, but it can also be used in order to calculate. So there is another technique. This is I'm always. There's another technique which I just wanted very briefly to say. So the minds people from the Max Planck for nuclear physics, they have also developed a different technique, which is not only ejects the ions onto the axis and looks at the time of flight, but they have made a measurement which has a phase sensitivity. Okay, so that they can really detect the ions on different phases on a microtangent plate with a spatial detector, which gives another term to this mass resolution and which can help them to go to have even a factor 10 better than what they can do by time of flight. Okay, so let me just introduce a few experiments. So I really like to introduce some of the experiments which are made with single ions. As I said before, there's many mass spectrometry things. There's many experiments in mass spectrometry which are made at these large facilities like Isolde and others, and they're all working with more or less refined techniques of what I just shown you in panning traps. And there's at Isolde in particular, there's a number of, well, okay, I say at Isolde because this is maybe what I know the best, but there are other facilities. And so I must admit, I don't know all the facilities, but I know that there's a number of very high resolution mass measurements which are made in particular for all which is exotic and rare isotopes. So the trap can be used for more fundamental measurements, which are still frequency measurements, because this is what we measure the best. And this is one of the slides of Stefan Ulmer. So you see what Stefan has put in here is the ion in this trap. And I can maybe, I think this is one, oh, okay, I've been signed out. Okay, sorry, I've been signed out. But while I sign out, I will maybe, I can go, I have a different slide, which I can maybe, I will make it on the blackboard. What I've showed you until now was the hyperbolic panning trap like this, okay? But as for the Paul trap, you see, this is not very practical, okay? You want to put your, you want to create your ions or shoot them in there somewhere. You have to have some holes in the electrodes or things like that. And this, a structure like this with a ring, which is a closed ring, is not very practical. So what many people use, and I have a slide later on, which I can show you, is a trap which is more or less like this. Okay, which has a ring, okay, in here. This is the ring. And this is the end caps where you put on your DC voltage, okay, between these end caps, which are rings too. But if you have a trap like this, okay, which is only stacked rings, that can allow you to introduce your ions from one part, or your electrons, or whatever you want to, or from the other part. You could even shoot the laser in there. And as for the radio frequency trap, this trap will work more or less, will have the same properties as an ideal panning trap, okay? Maybe not in its complete volume, but at least in the inner part. And if we're working with very small numbers of ions, we will not see the difference, okay? And so for practical reasons, these traps are used a lot in what I'll show you. And these, and maybe in a more sophisticated way, are called Penning-Malmberg traps. Well, Malmberg is, well, I come back to that, but this is a modified panning trap, and it's a very open trap, and it consists of stacked rings. And you will see that in Stefan's slide here. It consists of stacked rings. You have an inner ring, which is the trap, and then the two outer ones, which are the ones where you put the DC on in order to trap. And you see there are still some other electrodes out there which are grounded in order to shield what you have in there, because of course all these potentials are subject to all the perturbations which fly around or which are around this trap. And so in order to have a very neat potential, which you see, by the way, here, okay? So this is, well, again, once again, as I showed you, the modified cyclotron motion, the axial motion in this way, and then the orbiting around this, these B field lines, okay? So what is used if in these measurements, which measure the charge of a mass ratio, is this, this relation, and what we've seen before, okay? And you can very easily then measure the frequencies of the different particles which are in that trap. And if you measure these frequencies, you can compare, for example, here, this is the comparison of the mass charge to mass ratio of the proton and the antiproton, okay? And you can see that there is really the resolution of the different frequencies which can be made in these experiments which, well, like I said, this is Stefan's slide, and he said, these are very simple experiments. The concept is very simple. If you see them, they're a bit more complicated because these experiments are in particular very, they're subject to noise, everything which is electric noise, of course. And so they have to be shielded in a very good way, and they have a very, very good low noise electronics in order to be able to measure these frequencies. But it's true that the concept is very simple, which is just the measurement of the frequencies of protons and antiprotons. And so this is the measurement which has been made for in this trap, for example. You see that here there was a scheme on the slide before, but this is the real trap. So you see, this is really a stack of ring traps. Okay, you have an upstream park electrode where you can park the ion or the particle you don't work on. You have something which you can. Oh, sorry, but these are. No, will it come back? Will it come back? It will. Here we go. No. Okay, this is the. So you have a park electron here, you have a park electron or reservoir electron here. There's also in this setup, there's a reservoir trap because at a certain moment, Stefan and his group, they had made a reservoir also of antiprotons so that they are independent of the antiproton production. There's a measurement trap in the middle. And what you can think in this experiment like that, you come in with your proton, which you have in a reservoir like that. You come in here, you make the measurement of the frequencies of the proton, of all the frequency and emotional frequencies of the proton. Then you shuttle it back to this reservoir. You come in with your antiproton and you measure in the same trap. Because as you've seen before, that's very important. You need the same experimental configuration, okay? So you would want to measure the same frequencies in the same setup so that all the imperfections, all the environmental influences are the same. And this is what's done in a sense, in a setup like that, okay? So really something where there's antiprotons from one side and then protons from the other side. And this is the comparison of the charge to mass ratio of the antiproton to the proton. And this measurement has been made to 10 to the minus 12 over a number of months. There is a number of that has been measured for, you see there are 35 measurement days. And this is the most precise test of CPT invariance with baryons. I mean, this was very, very close, consistent with 1 to 10 to the minus 12. A measurement which is more complicated in these traps with single ions is not to measure the mass, but to measure the G factor and to measure the G factor of the bound electron. I mean, this will bring you back to your atomic physics lecture from the very start. You remember that the electron is bound to the nucleus, and if you want to study this electron, then we can measure the magnetic strength of the bound electron with a G factor. And the electron acts like the spinning top in the magnetic field with the frequency, which is the Larmor frequency, okay? So the Larmor frequency, which I put there. And then the electron, as you've learned, can be in the spin up or in the spin down state. There's nothing new for you. You've all had those atomic physics lectures, maybe already a few years ago. Now, how to measure that? The measurement of the Larmor frequency, even in a well-known magnetic field, is not easy, okay? Because it's nothing we can measure directly, okay? So if you want to measure frequency, there's nothing what we can measure directly, but we want to know this value. What we can measure more easily is the free cyclone frequency to determine the magnetic field, okay? We can also, if we say, what I told you before is we measure the mass of something, we measure by measuring its frequency in the magnetic field, okay, in a given magnetic field. We can do the other way around. If we have a particle we know the mass of, we can measure its frequency in a field that we want to calibrate. If we know the mass, if we measure the frequency, we know the B field, okay? It's a way to measure the B field. So measuring the cyclone frequency for a given mass gives us the B field. Now, how to measure the Larmor frequency? What we want to measure is we want to measure the ratio, largely the ratio of this Larmor frequency with the ratio of this cyclone frequency. Okay, this is something which is in order to determine the G factor, which is something. This is the factor we want to measure. Now, how do we measure that? This is a bit more complicated because the Larmor frequency, as I told you, cannot be probed directly. Okay, cannot be measured directly. But you remember that an electron can have spin up and spin down, and we can excite that with microwaves, and we can go from spin up to spin down. Okay, but how can we know that we have made a spin flip? How do we know that we go from spin up to spin down? What is it? What we can measure to know that there is this transition which has been made. So remember this, huh? You remember this? Remember these guys, Stern and Gerlach, who had this very nice inhomogeneous B field. I remember that well because there is a large magnet at the University of Tübingen where I made my studies. And they always told us that this was the magnet of Stern and Gerlach, which is an inhomogeneous B field. You know, you look at this field and you see there's something which is peaked there and something which is round there. That cannot be very symmetric, but that must be an inhomogeneous B field. And remember the experiment they made that in this inhomogeneous B field, there's only two states for the spins, and one is spin up and one is spin down. And we just use exactly this. There is a frequency difference. We can make a potential which is spin dependent in an inhomogeneous magnetic field. Okay? The magnetic field we want to have is inhomogeneous. That we will not touch our trapping, not our trapping magnet. Okay, so we do have the panning trap. The ions are still orbiting around their B field lines slowly every day. Okay, and what we do is we will create what we call a magnetic bottle. That means we just add an iron ring to one of the traps. You've seen these stacks. If you add an iron ring to one of the traps, it will completely mess up the magnetic field. Well, mess up. It will completely modify the magnetic field, okay? And it will create a perturbation, which is a magnetic bottle, which is something which is not foreseen and which will perturb the magnetic field. So by adding an iron ring, a ferromagnetic ring to one of the traps, we will create an inhomogeneous magnetic field. And you will see in this inhomogeneous magnetic field, this is a spin-dependent potential. Spin up and spin down will not see exactly the same potential. They will feel, spin up will feel the blue potential and spin down will feel the red potential. And so by measuring this, okay, having different potential means having different motional frequencies, okay? So by measuring the different frequencies, we can know if it's spin up or spin down. So by doing this experiment in an inhomogeneous magnetic field, we can see if there has been a transition from spin up to spin down or vice versa. And this is a way to really measure the Larmor frequency because you will shine in your frequency and you will measure for each frequency you put in, you will measure, what's the probability of the spin flip? And this is a very, very long measurement, okay? So the measurement is done in a setup like that, always the same thing, stacked rings of ions. There is the analysis trap, there's the precision trap for measurement. This is a very nice thing. You see the analysis trap is the one with the ferromagnetic ring on that, the magnetic bottle. So there are microwaves which are brought in from one side, and then there's a measurement cycle where the ion is excited by the microwaves, it's analyzed, we're looking for the spin flips, it's then shuttled to the precision trap, there is a measurement made of the frequency, there's another microwave irradiation which is made, there's a transport made, and you see that one measurement cycle in this one single atom or proton, one single atom experiment takes like quarter of an hour, okay? So, and if you want to measure that with a large precision, you need a long time, a quarter of an hour, okay? So this measurement is a very, very long measurement. And it's what I can show you is the results. This is all, as I said before, from the base group. So the G factor of the proton, the G factor of the antiproton, and these are the experiments which are from 2017. You see, these are the measurements from base, either made in a single panning trap or in 2 different panning traps. And the fractional precision of these measurements of the order of, can reach something of the 10 to the minus 9, the very best measurements which have been made on these G factors of antiprotons and protons. Okay? It's important for us today to know these factors with a very good precision. This is the fundamental physics part. Knowing the fundamental constants, knowing the G factors with high precision will also help to go to have better theory approaches and go further then. And then there's still, I mean, the base people, they always say these improvements, it's not I who put on them. They say we can make these, still make improvements on them, on these measurements, and they are still looking forward to have better experiments on that, to really measure the G factor, which is a really fundamental issue in atomic physics. Okay, but we can put more than one particle in that. We can put more one particle, and here is this my slide about the modified panning trap. It's a bit late, but there it is. Okay, so this is, like I told you before, we only have the cylinder here, and then the 2 cylindrical electrodes, which are the DC electrodes. Okay, and what is done in, so in the experiments I showed you with a single particle, they are really stacked rings, one above another, and used like that. What is used if we are working with a plasma is something which is a bit modified, and you will see why this is modified. If we put in a large number of ions in these sort of traps, okay, what you've seen from the motion is that the ions will still orbit around their B field lines, but the whole plasma will rotate. Okay, you've seen this motion which goes every single orbit and the large orbit of the plasma. And if you have a thing like that, if you have a large cloud of ions, the whole plasma will rotate around the z-axis. Okay. In this experiment. Okay, so there will be, oh, it's already put on there, there will be the rotation of the whole plasma around this. What is done in these experiments, in particular those I will present you, which are those of the San Diego group, or maybe the experiments I will show you are those of John Bollinger at NIST and his group, and some of the antimatter experiments. What people do is they will segment this ring into different segments, in 8 or more different segments. Some are 4 segments. And what you can do if you have a segmented trap like that is you can manipulate the angular momentum of that rotating plasma. Okay, you can either add or remove angular momentum. You can really try to, you can put a torque on the plasma also. You can try to be resonant with the plasma modes. Okay, and so the way that these things are put into place is to put on, to have this segmented ring of the plasma, and then to be able to put different drive electric fields around this plasma in order to excite different motions in that plasma. Okay, so as I put on there, you can either apply torques, or you can also compress the plasma, or design certain plasma modes by putting on different electric field excitations on this electrode. Okay. So this is what we call the Penning-Mollberg trap. And what I did not introduce yesterday, because I said I will not talk about laser cooling, about cold lines, I didn't even talk about the gamma factor, which is something which I have to introduce now, because this is important if we talk about plasma. So if we look at the energy in a plasma, this important factor looks at the potential energy between the neighboring ions, compared to the ion thermal energy. Okay, so what is really the energy of this plasma? And this gamma can be calculated by something which is, of course, I will not get used to this. There are too many. Yeah. No, no. So here we go. So we have the charges, of course, we have the KBT, the ion thermal energy, and we have the Wigner-Seitz distance, which is something which is well known. I mean, the distance between the ions in this plasma. Okay, so, and which can be also calculated from the number density of the plasma that you're looking at. Okay? So in general, if we have a gamma which is larger than 1, we can call it a strongly coupled one component plasma. And if we have a very large or almost infinite one component plasma, and you will see what infinite means, then what you will roughly be saying is that if gamma is larger than 2, then you have a sort of liquid behavior. And if it's something around 170, and this is there's an error bar around that, then you will also have the transition from the liquid phase to the solid phase and to a BCC lattice, and you can really see crystal structures of these large clouds in the Penning trap. Yes. In case of electrons, repeat please. Yes. Yes. But no, yeah. So there is a discussion about that Wigner crystallization, because you look into the normally you look into the potential of the how can I tell it? You can say that we will not look into the only thing I introduce is the Wigner-Seitz distance there. I will not go into the Wigner crystallization, which is very similar to the crystallization of the ions in that trap, but there are some differences. But we can talk about that later. It's a special case about that. Here we go. Why is going to BCC? You will see. Because there are others. There are others. So John Bollinger has made this very nice image where he said, so this is the plasmas, all the plasmas you know, in nebulous, in magnetic fusion reactor. You have here the number density and here the temperature. So the fusion reactor will be somewhere high up here, and flames will be low down here at temperatures which are not very high. And the laser cooled ion crystals are very low down here. You know, they're below this. They are below this graph because the temperature is something which is of the order of milli-K, and the number density is something around here. So compared to this very well-known graph about strongly coupled plasma, the laser cooled ion crystals are below this graph. Okay. So now, if we look at what the Bollinger group has made. They have been the first to look at these structures, in particular to see if we are crystallizing, can we measure how do we crystallize? What is the crystal structure that we can measure? And so normally, if you come from crystallography, then you know that you do that with Bragg diffraction, and that's what they did in their Penning trap. Okay. So this is already 25 years ago. With very large ion clouds and a Penning trap, which is like this, always the same thing, the very cylindrical approach there. A laser beam shining through the trap from below, and then making this Bragg diffraction on this crystallized crystal, on this ion crystal, and looking at the Bragg diffraction of that. Okay. So if we look at this, this is the first image. So this is this is an electrode, okay? So don't look at this. And what you see here is, you see exactly what I told you before. The plasma is rotating, okay? The crystal is not blocked. There is a rotating plasma, so the Bragg diffraction, you see that? It's the integral of the rotating plasma, okay? You can have the different distances here. And you can see this is very well resolved, but the plasma in the panning trap is rotating. And so this is the first approach. Okay? But you can strobe that. I mean, you can look at you can make a stroboscopic resolution. You can see what is the frequency of rotation, and then just take the and then trigger on that frequency. Okay, and then you can start having the first real Bragg diffraction of a. You see, this is the first idea of a Bragg diffraction in this trap to see what is the crystal structure they are looking at. The idea of looking at these crystals is that in a panning trap, you can make very large ion clouds. You don't have micromotion. You can go far from the center, and the crystal will have conditions which are very close, if they're to the center or not. Okay, so the idea is really to go to very large systems. You can do that in the system, and the goal would be to reach something which is at least of the order of 50 Wigner-Seitz distances. So in order to be able to get rid of all the edge effects, to have a really bulk crystal and not a surface. Okay, and so this is the follow-up of that with a really much larger crystal, and you see, maybe you don't see everything on that, but I can tell you that I have a nice zoom in there. So this is the zoom of two of these crystallized beryllium ions in that panning traps. And you can maybe see it already from there. The structures are not the same. In fact, the bulk structures are not the same. We can look at it afterwards. There are different bulk structures. In fact, you can, by tuning the different frequencies in that trap, you can tune the crystallization structure, and you can go from different crystal structures to go from BCC to FCC. There are different crystal structures, and this is the objective of this experiment, trying to look at crystallization at structural phase transitions in order to be able to look at how does it behave. But in order to do so, you have to be sure that you get rid of all the perturbation effects. The crystal has to be very large to have a bulk behavior. Okay, and so I find this very beautiful. This is a very beautiful experiment looking at the Bragg diffraction. I stop there. I will stop here. No, I will stop here. There are other crystals. Somebody asked me yesterday about crystals also in a panning trap. These are images of small crystals in a panning trap from the Imperial College. And you see that they all rotate. In the panning trap, things are always rotating. So putting up these sectored electrodes, like I've shown you, allows one either to trigger on that rotation frequency or to anti-trigger onto that rotation frequency, okay, and to induce some very special modes by using the segmentation of the electrodes. But in principle, all the crystals in the panning trap rotate, and you see that wonderfully what our colleagues from Imperial College made on calcium ions in the panning trap, 4 different trap parameters. And I find this is a very, very nice collection of rotating crystals in the panning. And just to finish, because the chairman says 5 minutes, but I will faster than that. So just to finish off, this is, as you see, this is a trap for making antimatter. Okay, this is the alpha trap from the alpha collaboration. Alpha is one of the 6 collaborations working at CERN on the antiproton decelerator. Okay, one is base, the experiment I showed you from base, because antiprotons is, you can not have them somewhere else. You need to be at CERN to have antiprotons. Okay, so and so alpha is one of the collaborations at CERN. One collaboration which has been very successful. What they do is, in this stacked trap, I mean, everybody works with these stacked Penning-Malberg traps in order to first trap antiprotons from one side, positrons from one side, overlap the 2 traps in order to put antiprotons and positrons together in order to make antihydrogen. And the antihydrogen is then trapped in a magnetic trap because the antihydrogen is neutral. Okay, so that's trapped in a different trap. But the idea in these traps is always to use these panning traps where you can bring in positive and negatively charged particles, okay? In a Paul trap, that's very complicated. You've seen that on the stability diagram. You cannot have plus and minus charged ions at the same time. But in a panning trap, you look at the orbits and you can have these nested traps which do have positive and negative ions at the same time. And this is used by the alpha calibration. So just to finish, there is, I love this very much. This is a very neat experiment on laser cooling with anti-hydrogen. And this is, I mean, for all the people who come from atomic physics, this is really something, I find it very instructive because this is laser cooling the hard way. Really, if you read their paper, if you look at the experiment, I think this must be from the very beginnings what it was in atomic physics. It's very difficult to make these antigen hydrogens, okay, antigen atoms. They have like 30 atoms per every couple of minutes. So to accumulate them to have 1,000, that needs already hours. And then they laser cool them for 6 hours, okay? And they have this narrow width pulse Lyman alpha laser, which is a laser at 121 nanometers. So that's really hard work. But if you look at this beautiful curve, they have managed to laser cool anti-hydrogen atoms in these traps. And this is really an experiment which works very nicely. They are about to measure the first experiments on gravity sign in order to give an answer of if antimatter falls up or down. Most of the people have an opinion on that, okay? But they are very successful in doing that. And I find this is a very nice experiment where you can see, and it's a very nice paper. I can really encourage you to read it. You can see every step of this, how the spectroscopy is done, and it's very instructive. So I find this is a very nice experiment to finish on, in particular, as today they do have this they have some very nice experiments, but their aim is really to make anti-hydrogen spectroscopy as good as hydrogen spectroscopy, which is one of the best measures atoms we have. And they're on their way to that. And I think that I don't know if they ever come to that same precision, but that's their objective. So in order to conclude, and before the chairman will eat me up, so I've talked about trapping of charged particles. I hope that has given you some insight on what are the basic techniques in order to do precision measurements. There are different techniques which we have to use in order to be able to trap, to manipulate, to look at the ions. And what you've seen is that concerns all charged ratios. It concerns all particles as long as they're charged, and it's easy to make a neutral particle a charged particle. And it concerns all sample sizes from 1 particle to clouds of 10 to the 9 ions. You can combine this trapping with everything you want. It's like a pizza, okay? You put on salami and cheese, and you could put on laser cooling, photoionization, any detection you want to, metrology, and combine it with other traps, combine it with other techniques. So it's a very versatile tool in order to go to very high precision measurements. And then you have, like I said yesterday, a large panorama of applications from quantum information over cold chemistry. You name it, you have it in ion traps. So I think that with this, I would like to finish. I would say, even for your experiment, there will be a trap. So, and don't forget to think about that. Thanks.
Thanks. Yeah, we have time for right about 1 question. So.
Thank you very much. That was fantastic. I have a question and a comment.
Okay.
What shall we start with?
Start with a question.
With a question. Can you explain the rotating wall business you had on a couple of slides before for non-neutral plasma?
Okay, maybe not the details of it, but the rotating wall is a way to trigger to trigger the electric field, which is put on the sectored electrode, and it's a way to either induce different modes in the plasma, like these trivial trivial piece gold molds, and or to compress the plasma also in a certain way. What the San Diego, there's the group who works on that mostly is a San Diego group, Francois Anderek and Dan Dubin. And what they use it for is a fact is really to try to compress the plasma to certain sizes, and also to have to certain densities in order to be able to have the densities they want, and to create the plasma modes they want.
Basically, it's a rotating field.
Yeah, it's a rotating field. Yes.
So my comment is about this apparent difference between the mass of proton and antiproton. In fact, the mass of proton and antiproton are equal to better than 7 parts in 10 to the 10, I believe, or something like that. And I believe what is the explanation of the difference in your slide is that the base is using base collaboration is using negative hydrogen ions as a proxy for the proton. So there is 2 electrons that you need to add, because otherwise it would be a completely different, different polarities. It wouldn't stick in the same.
So we have to look into that, because Stefan is not giving, if it says a proton mass, it's a proton mass.
That's my theory, for because it
your
was
theory, but
at
I
that level,
would
10 to
not-
minus 3.
but we
Okay,
have
I
to
think
look it up.
let's continue the debate after this thing. So let's give another big hand to Martina. And then we have one little thing. Can I invite Shubhanadi wants to come and give this to this honor?
Thank you very much. Thank you. Beautiful. Thank you very much. This is a very beautiful thing. Thanks a lot.